Unit cells are the repeating units of a crystalline solid, or I sometimes use this term that I just made up, continuous atomage. A unit cell is a building block of a crystalline solid. Think of one building block and then think of putting many of those to the left and also to the right and up above and below and in front and in back. These unit cells go out and propagate in every direction three-dimensionally. There are three main types of unit cell. The primitive or simple cubic, which has an atom at each corner. This box that I've shown here, if we want to count up how many atoms are actually inside that box, if we look at one of these atoms, the one in the upper left and in the front, with a little thought, you can convince yourself that only 1/8 of him is inside the box. He's been bisected by three planes. That is, he's been cut in half once, in half twice, and in half a third time. That's 1/2 times 1/2 times 1/2. So only 1/8 of him is inside the box. Now, if we count how many atoms here, there are 8 of them, and each of them have only 1/8 of them inside that box, which gives us a total of one complete atom inside that unit cell, inside that box. Now, a body-centered cubic starts out kind of similar to a primitive or simple cubic, with one exception. If I draw a line from the front upper left to the back lower right, and then I draw another line from the front lower left to the back upper right, and if I draw a third line from the back upper left to the front lower right, those lines meet right there. And right where those lines meet, there's another atom there. How many total atoms inside a body-centered cubic? Well, we know that the primitive part of that configuration gives us one atom inside the box, and then the entirety of this one is inside the box. I've just drawn him bigger so that he's set apart from the rest, which gives us a total of 2 atoms per unit cell for a body-centered cubic. The third kind is a face-centered cubic, and I've drawn that a little bit bigger because it's a little bit tougher to draw. There's more going on in a face-centered cubic. In a face-centered cubic, there is an atom in the center of each of these 6 faces of this box that I've drawn. So if I put an atom on the top face and another atom on the bottom face, I'm going to draw a line between those, and I'm just coloring them different colors so we can distinguish them. If we put another atom on the left face and another one on the right, and then we put another atom on the front face and one on the back face, we can connect them there. There is our face-centered cubic. Now, how many atoms are there in that face-centered cubic cell? With regard to the ones that are black colored here, that's 1 atom. What about the blue ones? How much of this blue atom is inside the cell? And the answer is half of him, and half of this blue one. So that's a second atom that's in the cell. Same thing with the reds. Half of this red, half of that red. Now we're up to 3 total. Half of this green, half of that green. We're up to a total of 4 atoms per unit cell. Roughly equal-sized spheres, such as those in metallic solids, are arranged in one of several configurations. These configurations are collectively called the close packing of spheres. In a given layer, the atoms are arranged such that each atom in that layer is surrounded by 6 others. This is called a close-packed layer, and it looks like this. The atom that we're interested in is the one in the middle, and he's surrounded perfectly by 6 others. You can think of these as 7 pool balls and how nicely they fit together. Face-centered cubic cells, which we met on the previous slide, which have 4 atoms per unit cell. Face-centered cubic is equivalent to a close packed repeating configuration of ABC, ABC as opposed to AB, AB. Now let's explain that very briefly. If we are looking at these atoms from the top, in other words, think of these as 7 pool balls. Okay, and now we've got an 8th pool ball and we want to set it on top of the stack. If we set it right there, the 9th pool ball has to go there and the 10th one has to go there. Let's imagine we can put 3 pool balls on the other side. Isn't it true that those 3 pool balls on the other side that are touching this atom of interest in the center, the 3 pool balls on the back side, what's on the back side of the screen, can either be right below this one and this one and this one, or they can be centered right here, I'm pointing with my laser pointer, and here and here. Well, if the 3 atoms on the back are centered below this one and this one and this one, then we have the AB, 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 AB pattern. But if the 3 atoms on the back side are centered right there and there and there, then we have an ABC, ABC pattern. The coordination number for a packing pattern is equal to the number of equidistant nearest neighbors for any atom within the matrix. For these particular packing arrangements, face-centered cubic, we're going to do the same thing we did before, where I've colored the atom of interest black. Let's put 2 more pool balls, one right there, and then we have to put 3 on the back side that are also touching this black atom. This black atom will still be touching the 6 in its own layer, plus 3 on our side of that atom, and then 3 more on the back side. That's a total of 12. For body-centered cubic, the one that we're interested in, let's say, is this one in the middle, and how many equidistant nearest neighbors does he have? And the answer is 8. All 8 of these on the corner are equidistant nearest neighbors. How about the primitive or simple cubic? Let's consider that atom right there. How many of his neighbors are nearest and equidistant? Well, not the ones that I've crossed off with blue X's. Those are not nearest neighbors. There's a nearest neighbor, there's a nearest neighbor, and there's a nearest neighbor. But isn't there also one right up here that is above that atom, and there's one to the right of that atom, and then isn't there one out here closest to us also? In other words, the coordination number for primitive or simple cubic is 6. For unequal sized spheres, sometimes the larger spheres assume a close packed arrangement, and then the smaller particles fit into the spaces in between. Let's look at this picture on the left here. If these are the larger atoms, they assume sometimes a close packed arrangement, but if we have, say, an alloy that has another atom that's much, much smaller, or maybe some sort of ionic substance where the other ions are much, much tinier, they can sometimes fit into these little spaces. You see how there's a little, you can imagine there's a little space under this ball, and if the atom or ion is tiny enough, he might be able to fit in there no problem. Like there, and like there. Let's summarize unit cells. 1. There are 3 main types of unit cell. The simple cubic, which has 1 atom per unit cell, the body-centered cubic, which has 2 atoms per unit cell, and the face-centered cubic, which has 4 atoms per unit cell. You'll notice that with the face-centered cubic, there is an atom on each of the 6 faces. And with the body-centered cubic, there is an atom right in the middle of the body of the unit cell. 2. In a close-packed layer, 1 metal atom is surrounded by 6 others. There's our atom of interest, I've colored it maroon, and in a close-packed layer there are 6 other atoms that go around it perfectly. Of course, the next layer is above this one, and 3 of those atoms will be touching this maroon one. And on the back side, there's another layer, 3 atoms of which will be touching that maroon atom on the back side. And 3, the coordination number is the number of equidistant nearest neighbors an atom in a matrix has.